Hello, everyone. Today we're here to talk about the LeChateliers principle and its relationship to equilibrium. Thanks for joining. The LeChateliers principle is about if we have a system at equilibrium and we do something to it, what will happen? So it says if a change is made to a system at equilibrium, the system will respond in such a way as to minimize that change. And we've got all kinds of examples today of exactly what that means. If you remember when we first started talking about equilibrium, we talked about this wonderful little high school here. So let's pretend for a second that this high school is in an equilibrium state and it really behaves the way chemical equilibrium systems do. So it's going to follow the LeChateliers principle. So at first, remember we had no couples. We had 300 single girls, 300 single boys. They started forming couples. We reached this equilibrium state where the amount of single boys, single girls, and couples is staying the same. It's dynamic. Some couples are breaking up and new couples are forming, but overall these numbers are staying the same. So let's just assume there's some magical property that's holding everything into this proportion. So remember, I believe in the first example we said that this high school was on a moon base. So a few more boys fly up to the moon and join this high school. Well, the system then, we've messed it up. We've added a few more boys. So how is the system going to fix that? It's pretty simple. These young ladies, they see a few of these new boys roaming the hallways. We're going to form more couples. So notice what happens here. When we form new couples, we've added some more boys, so our system's thrown out of equilibrium. Our system's going to try to minimize that. There's too many single boys in the system. It will fix that by causing more couples to form. And notice what happens. The amount of couples is going to go up a little bit, and the amount of single people is going to go down a little bit, because you can't form new couples without having less single people. If you add more girls, same thing. Some of these young men, they see some of these fresh young ladies roaming the hallways. Well, again, we're going to shift. As you'll see, that's the term that's used. We're going to move to the right side. We're going to form a few more couples. And, of course, in the process of forming a few more couples, we're going to have less single people. So that's going to bring us back to maybe not the exact same balance, but basically the closest thing we can get to these proportions that we see here. Adding more couples, maybe some of these couples come up together. They meet on the moon rocket ship, and so they join the high school as a couple. But you know what? As oftentimes, I think this is kind of analogous to when a couple goes off to college together. Maybe they see this brave new world of single people. If this high school worked like equilibrium, we would have too many couples then if we added more couples. We'd have too many couples in the system. We'd have to eliminate those couples, meaning those couples would break up. And so we'd say shift to the left, as we call it. The number of couples would go down, and the number of single people would go up. And that's really exactly how the LeChateliers principle works. So you're going to hear me, and have heard me already, use the word shift quite a bit. What it really means when we're talking about chemistry is that either the forward or reverse reaction will temporarily speed up to return a reaction to an equilibrium state. So we've got a reaction that's at equilibrium, we mess with it, we add something, we take something away, we do whatever. The system has to reestablish equilibrium. So if you have an equilibrium and you add something, the system is going to shift away from that side. You've got too much stuff. You've got to remove it by reacting it, basically. That's the way to get rid of it. If, on the other hand, though, you remove something, a system is going to shift towards that side to make up for the lack of stuff. You're basically going to make more of it. So this can be confusing for sure. We're going to look at lots of examples to see exactly what I'm talking about. But bottom line is the system is always, whatever change you make to the system is always trying to get back to that equilibrium however it can. So for instance, take this reaction right here. Nitrogen plus hydrogen making ammonia, NH3. So let's say initially I mix nitrogen and hydrogen in this fancy little vessel here. I let them start to react. They go back and forth. But then after a while, we reach this equilibrium state where all three amounts are staying steady. Now, if I then take into this system and I inject some more hydrogen, for a moment, the system is going to be out of equilibrium. There is too much hydrogen in the equilibrium system. So it needs to eliminate that hydrogen. So what will happen is the reaction that goes in this direction towards the ammonia will speed up a little bit. It will make more ammonia, and in the process of making more ammonia, you can't make more ammonia without using up the hydrogen. So we will use up that hydrogen to make more ammonia. The reaction will shift to the right, as we say. So here we have time. It goes up because we added some hydrogen. The reaction will try to get back to equilibrium. So notice that the amounts of hydrogen goes down and the amounts of nitrogen goes down, both of them, and the amount of NH3 goes up. Because as we shift in this direction, we've got to react the hydrogen, we've got to react the nitrogen to make more ammonia. So the amounts of both of these go down while the amount of ammonia goes up, and then we get back to a new equilibrium state. Notice it's not exactly the same as the first one, but it's a new equilibrium state that's been reestablished. So that's what LeChateliers' principle says, is the system is going to find a way to adjust for any change that you make and get back to equilibrium. And the bottom line is when you add something to one side, it's going to shift away from that side. If you remove something from one side, it's going to shift towards that side. Here's another example really with the same reaction, nitrogen, hydrogen, ammonia. Here we have a mixture of all three gases that are at equilibrium. Looks like there's two little ammonias. We add some nitrogen. So now there's too many nitrogens. It's not at equilibrium. The way the system can get rid of that nitrogen is by reacting some of it with this hydrogen. So we're going to make a bit more ammonia. There's 1, 2, 3, 4, 5, 6 nitrogen molecules here. The system's going to shift. It's going to make a bit more ammonia. Now there's 1, 2, 3, 4, 5. So it's eliminated some of those extra nitrogen molecules by shifting towards the product side. So here's an example. Here's an equilibrium reaction. SO2 plus O2 yields to SO3. So if I have a system that's at equilibrium and I add SO2, what's going to happen? Well, if I add SO2, there's too much SO2. So I've got too much of this. The system is going to shift to the right, meaning the amount of SO3 is going to go up, and the amount of both of these is going to go down. After that point that I add it, the amount of SO2 is going to go back down again. So we call that a shift to the right. Adding SO2 is going to cause a shift to the right. That's going to shift this way. Removing oxygen. If I remove oxygen, I need to make more oxygen. So the system's going to shift towards the side that I removed it from. That's going to cause a left shift. Adding SO3, if I have SO3, I have too much SO3. So the system's going to shift away from that side. That's going to be what we call a left shift. Again, just notice when we add something that's on one side of the reaction, it's going to shift it away from that side. If we remove something, it's going to shift it towards that side. When you think about the shifting, it's really handy to think of it like a teeter-totter, where this is the fulcrum of our teeter-totter. If you say you shift to the right, so if I say I'm going to shift this way, what I mean by that is the amount of this is going to go up, and the amount of both of these things is going to go down. So actually the reaction going in this direction speeds up a little bit, meaning the relative amount of this goes up and the amount of both of these goes down. And if you think about it, it has to be that way. It's like when you push down on one side of a teeter-totter, the other side goes up. It's the same thing here. If we want this to increase, if there's going to be more of it, there has to be less of both of these. It would be physically impossible to make more of this without having less of these. It's just like you can't form a new couple without having less single people. It's the way reality works. If you're shifting left, it's exactly the opposite. If I'm shifting to the left side, the amount of this is going to go down, the amount of both of these is going to go up. So pressure has an effect here as well. Let's just spend a second just kind of talking about pressure. So you could have, here's our same reaction with nitrogen plus hydrogen to make ammonia. You could have a reaction going on in a piston. we think back to the gas laws, you could change the pressure in that piston by increasing or decreasing the volume, and it's an inverse relationship. If you decrease the volume, the pressure is going to go up, and vice versa. If you increase the volume of the piston, the pressure is going to go down. There's another relationship. More moles of gas means more pressure. That's a direct relationship. I mean, if you think about it, if I took this piston, I injected more gas into it, of course, the pressure would go up. If I took some gas out of it, the pressure would go down in there. You know, when you pump more air into a football, the pressure gets greater inside the football. It's just, that's the way it works. So I just wanted to remind you of those relationships so we can think about this correctly. So if you've got an equilibrium system with gases, and remember, LeChateliers principle is all about trying to minimize whatever change you're doing. So you got a little thing sitting there, it's an equilibrium system, all happy, you know, cheerful, going about its day. If you change the pressure, it's going to try to counteract whatever change in pressure you do. So in equilibrium systems with gases, if the pressure is increased, the system can help decrease the pressure by reducing the number of moles of gas, and vice versa. And I'll show you some more examples of what I'm talking about here. So if you take something and you increase the pressure, the system is going to try to shift to the side with less moles of gas, because if it does that, it can actually reduce the pressure. So I push down on the piston, try to make the pressure go up. The gases will say, hey, not so fast. They will try to shift to the side with less moles, which will make the pressure go down again to counteract what I did. And the opposite is true at decreased pressure. If I make the pressure decrease by increasing the volume of the piston, the system is going to shift to the side with more moles of gas, because that way it can try to increase the pressure again. It can try to counteract this change that I made. So again, here with this example that we've been looking at, if you look at this example here, there's a total of 4 moles of gas on the left. There's 3 right there and 4 there. Understood 1 here, of course. That's a total of 4 moles. There's 2 moles of gas on the right. In the general reaction. Obviously, I don't always have those exact number of moles, but that's just the general case. So if I take that and I increase the pressure, what the system can do is it can shift to this side, because that side has less moles of gas, and if you make more ammonia, you'll actually reduce the number of moles of gas in the container and reduce the pressure, so the system can reduce its own pressure. So notice here, for instance, let's see, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 total moles of gas. Some of these nitrogens and hydrogens can combine, can shift this way, and now there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total moles of gas. So I tried to increase the pressure by pushing down on the piston. The system shift to make less moles of gas and actually can reduce some of that pressure. Now, it might not be able to completely counteract it, or there's a million combinations of things that can go on, but it's going to try to counteract that pressure change that I made. And the opposite is true if I took this piston and I expanded it. I pulled it up. If it was a bigger container, obviously it would need to be. I pulled it up. So now the pressure is too low, so the system would shift to the side with more moles of gas, which is, in this case, is the left side. It's not always going to be the left side. In this case, it's going to shift to the left side, the side with more moles of gas. So actually, to go back a second and sum up here a little bit, just a general statement. When you've got a reaction with gases, higher pressure shifts to the side with less moles of gas. Lower pressure is going to shift to the side with more moles of gas. If it's not a gas, none of this applies. This only works with gases, and when you're talking about which way it's going to shift, you got to look for moles of gas. Moles of other things don't matter because they're really not affected by pressure to the extent that gases are anyway. So heat energy. Heat energy also can affect the equilibrium state, can and does. So let's kind of remind ourselves of a couple of things. When we were talking about heat energy, remember, if you flip a reaction, you reverse the sign of delta H. Delta H of that's negative is an exothermic reaction, and when delta H is positive, it's an endothermic reaction. And if we flip a reaction, we flip the sign of delta H. So if a reaction is endothermic in one direction, it's exothermic in the opposite direction, and vice versa. So in these reversible reactions we're talking about here, they're endothermic one way, and they're exothermic in the other. So if you take an equilibrium system and you change the temperature, there's a few things that can happen. So if the temperature is increased, an endothermic reaction, meaning in the forward direction, the way we normally think of it, if you take the temperature and you increase it, endothermic reaction can use up some of that heat because it can shift to the right, it can do the reaction. The reaction is endothermic, so it takes in heat energy. So if you take an equilibrium system and you increase the temperature of it, endothermic reactions can shift right, and they can use up some of that heat energy you added. If the temperature is decreased, the endothermic reaction can shift left, which is the exothermic direction, to generate a little extra heat. So depending on what you do, again, the system can counteract this. And all that is exactly the opposite for an exothermic reaction. And this is definitely, out of all these things, this is the most confusing part. And you might be a little confused already, but we're going to look at some examples here. What's really useful is to think of heat energy as a reactant in an endothermic reaction, because remember, endothermic means put energy in, and a product in an exothermic reaction. And if you think of heat energy that way, basically you can just apply the normal rules of LeChateliers principle and everything will work out. So let's take a look at a for instance here. So we have this reaction. Notice it tells us it's exothermic. It says, what's the effect of adding heat energy? Well, all right, let's kind of think about what we know here. So it's exothermic. A couple things that tells us there. We know that delta H is negative. Whoops, that's a terrible negative sign, but hopefully you get the idea. So we know it's negative. We know it's exothermic. So one thing that I might do is to this side of the reaction, I'm going to add plus energy. It's hard to write with this. The reason I'm adding energy to this side is because it's exothermic. And like I said in the previous slide, it's going to be useful to think of heat energy as a product in an exothermic reaction. It's giving off energy here. And the advantage to doing that is if we think of heat energy as a product, then we can just apply the normal LeChateliers principle rules. So what is the effect of adding heat energy? Well, energy is on the left side. It's on the right side. So if we increase the temperature of this reaction vessel, that's going to shift us to the left. It's going to shift us to the NO2 side in this case. So at increased temperatures, we're going to see a little more NO2. What's the effect of removing heat energy? Well, heat energy is on this side. So if we remove heat energy, it's like we're taking something away that's on this side. So that would shift us to the right. That would shift us to the N2O4 side, to the more clear side. So temperature changes are going to cause a shift in one direction or another. Now keep in mind, if this reaction was endothermic, I would have put energy over here as a product, and the effect of both of these changes would be opposite. So when you're talking about how temperature changes affect things, you always have to think first, is this endothermic or is it exothermic? So we talked before, the equilibrium constant, they call it a constant for a reason, doesn't change with every little thing. The value of the equilibrium constant is changed only by temperature. That's, out of all these changes that we've talked about, none of them affect the value of Kc, but temperature does. So hopefully you can piece together the math of how this all works to kind of understand it. If reactions are endothermic, Kc values, the value of the equilibrium constant, is going to increase with increasing temperature, and it's going to decrease with decreasing temperature because higher temperatures encourage the formation of more product. So if we've got an endothermic reaction, we're thinking of heat being, so if we just have some reaction, let's just call it reactants going to products. If we've got an endothermic reaction, we're going to think of energy being over here. Call it En for energy. So at increased temperatures, we're adding something that's on this side. That's going to cause us to shift to the product side to have more product. And that also, if you think about our equilibrium expression here, products go on top, reactants go on bottom. So if there's more product at that higher temperature, this number also is going to be higher because it's going to increase the numerator and it's going to decrease the denominator. And if you're decreasing temperature, just the opposite, the Kc value is going to go down. This is for an endothermic reaction. For an exothermic reaction, it would be exactly the opposite. Now the energy is over here. The energy is over on this side. For an exothermic reaction. So at higher temperatures, we're adding something to this side. That shifts us to the reactant side at higher temperatures, which means the value of Kc is going to go down. Do you remember Sam Jackson in the other video, how super important it was that you understood Kc and like what it means? This is exactly what I'm talking about here. If you really understand Kc well and what it means, this should all sort of make sense. If not, it's definitely makes it a little trickier. So for exothermic reactions, Kc values decrease with increasing temperature and increase with decreasing temperatures because higher temperatures encourage the formation of more reactants. Now again, I know this can be a confusing topic. Stop, back it up, think about it a bit, ponder it. Of course, ask me questions if you don't understand. But that's the general process with heat energy. Okay, so catalysts. Recall that catalysts are things that speed up chemical reactions. Let's say you have an equilibrium system that you've been doing without a catalyst and you throw a catalyst in there. Well, that's not going to do anything. They do not change equilibrium values. They only cause you to reach equilibrium more quickly. Or if you, basically, I guess, a catalyst, you're always going to end up with the same amount of stuff that you would have gotten without the catalyst. You're just going to get there faster. You're just going to get to equilibrium faster. But overall, the equilibrium values are not going to change with a catalyst in any way, shape, or form. And the reason is because catalysts increase the rate of both forward and reverse reactions equally. They don't, since they speed up the reactions equally, they're not going to change one or the other. They're not going to cause any change in the proportion because both the forward and reverse reactions are increased equally. Okay. So we're just going to practice with this a little bit. I don't know if you're writing these down in your notes. I don't know that you need to write down this whole table. There's a ton of practice in your workbook. It might be more to your benefit just to kind of watch me work through this. So it says, consider reaction to equilibrium. Consider the effects of the changes below on the equilibrium reaction. What we're going to do is we're going to say in which direction will it shift. We're just going to write an arrow, right or left. And we're also going to say what's going to happen to these concentrations here. Are they going to increase or decrease? And also what's going to happen to the value of K or Kc or the equilibrium constant. Is that going to increase or decrease? So addition of A. So if you add A, when you add something to one side, it shifts opposite side. So it's going to shift away from that side, it's going to shift to the right. Meaning the amount of AB is going to go up. But it works like a teeter-totter. The only way you can make more AB is to have less of A and B. Now I know what you might be thinking. It says right here that I added AB. Why am I saying the amount of A is going to go down? What I mean is right after we add A, yes, we add A, so the concentration of A is going to go up. But I mean after that, as it goes back to equilibrium, the amount of A is going to go down, the amount of B is going to go down, the amount of AB is going to go up. The value of the equilibrium constant does not change. The only thing that changes that is temperature. Removal of B. When you remove something, the system's going to try to make more of it. So it's going to shift towards the side where B is, meaning the amount of A is going to go up. You can't get just more B. It's physically impossible because every time an AB breaks apart, it makes an A and a B, and the amount of AB is going to go down. And again, yeah, we remove B, so the amount of B is going to go down, but then it's going to rise back up again. That's why I'm putting an up arrow here. Addition of AB. When you add something, the system's got to try to eliminate it, so it's going to shift away from that side, meaning the amount of these are going to go up, these are going to go up, this is going to go down, this doesn't change K, this doesn't change K either. Okay, increase pressure. So we have the system at equilibrium, and then we increase the pressure. Notice there's 2, 1 plus 1 is 2, total moles here, 1 total mole on this side. So if we increase the pressure, the system's going to try to reduce that pressure by shifting to the side with less moles of gas, which is the right side. And in shifting to the right, there's going to be less A, so the concentration of A is going to go down, concentration of B is going to go down, concentration of AB is going to go up. Still no change to K. And lastly, increased temperature. All right, well, there's something very important here. Endothermic, meaning at least, when we say it's an endothermic reaction, we mean in the normal left to right direction. It's endothermic. So we can think of energy as being over here. So energy plus A and B make this. It's a reaction we've got to put energy into. So once we make that little leap, then this works like everything else on the table. Increasing temperature, well, temperature or heat energy is on this side, so it's going to shift away from that side, meaning the amount of A is going to go down, the amount of B is going to go down, the amount of AB is going to go up. Value of K is going to change here. We've made more product, or there's more product at this new higher temperature. There's more product. The bigger or the more product, the larger K is. So in this case, an increased temperature is going to make the value of K be larger, or the value of K will be larger at this higher temperature. If this reaction was exothermic, all of these arrows would be exactly opposite. It would do the exact opposite thing all the way around. Okay, so that's the LeChateliers principle. I understand it can be confusing. We'll definitely be talking more about it in class, and ask me questions if you have them. Thanks for watching, and enjoy your evening.